Good day, folks. Welcome to Bright Mind Academy, where we bring brilliance to every lesson. Now, in today's video, you're going to be looking at a new topic that is now introduced in grade 12, called a rate of reaction or reaction rate. Okay. Now, in this topic, we're going to be looking more on how particles collide during a reaction, a chemical reaction, to be more specific, right? So remember, this is chemistry. We're going to be looking more into the reactions, right? On how a chemical reaction occur. But now we have to look into a depth or during a chemical reaction, what happens that causes the reaction to occur effectively so. Okay, so now we call the theory that we'll be looking at now the collision theory. Okay, now before I just continue with everything, now we are remember, in a reaction we have particles, right? We have particles. Let's say this is an enclosed uh, chemical reaction. Now we have particles, right? So remember, for a chemical reaction to occur, those particles should do what? Now I'm telling you, those particles should do what? Should collide. Okay? Now for a reaction between particles, those particles should do what? They should collide. Okay, so that the reaction can occur. If these they are stationary like this, or they are not moving like that, there's no reaction, right? So for a reaction to occur, these needs to collide. Okay, these needs to collide, right? But now the most important part is that they are not supposed to just collide. They should collide effectively, so such that they produce an outcome that is going to be beneficial for us. Okay, they should collide, and the collision has to be effective. It should be an effective a collision that gives us the results that we are looking for. Okay, so as number one states, for a reaction between two particles of the reactants to take place. Okay, for a reaction between two particles of the reactants to take place. Now, the first one that we need the particles. Okay, the particles have to collide. Have to collide. That's the first one. Okay, it's fine. The particles have to collide. Okay, very important. Collide. Hence, we are saying it is a what? A collision theory. Okay, and what? Not only that they should collide, but they should collide how? Effectively. Okay, we are saying the collision has to be effective. Okay, yes, these are the two conditions needed for a reaction between two particles to occur, right? The most important part is that for the effective collision, what is it that is needed? Okay, now if particles, as I've drawn them before, for them to agree, we said if we are having particles like those, we need them to do what? To collide, right? We need them to collide. But can you see? So that for them to move from this stationary point, they need to do what? They need to have what? The enough kinetic energy, the moving energy that will move them towards one another. Okay. Now remember, already in a chemical reaction, from the video I recorded, uh, energy and chemical change, where we say this is a reaction and what. Remember, we talked about the minimum energy. Okay, the minimum energy, which is our activation energy. Remember, we talked about that energy, right? Remember, these inside here, they have EA, right? They have activation energy. Okay, the energy that is needed for the reaction to occur, they have it. But now we need more of the kinetic energy. Okay, we need the kinetic energy to overcome this activation energy, so that they can collide effectively. Most of them, if most of them have enough kinetic energy, they can collide effectively. Okay, if they have enough kinetic energy, that is, greater, or we need a kinetic energy that is greater or equal to the activation energy. Okay, remember they were stationary with that activation energy. Okay, so they have that little energy, they are moving. Let's say, okay, with this activation energy, they were moving, but they were moving slowly. Okay, they were moving slow. Now that we need what? A higher kinetic energy so that they can move fast. Why do we need them to move fast? So that the reaction can occur fast. Okay, and the effective collision can occur thereof. Okay. Another thing that we need, it is the correct orientation. Okay. Now the correct orientation, I always looked it like this. If I'm having, we do not know what is reacting, right? Like that. Let's say, okay, let's say, so this is us in a reaction here, okay? In that particular reaction. Now, remember, okay, if they just collide, can you see if this one was to collide with this one? There will be no correct orientation. They will not attach the way we want them to attach, right? But if you were to take this and get it here, it will do something like, okay, it will come and join like that, fill up that gap, okay? Then that part. So this is what you call a what? A correct orientation. The orientation should be okay, right? Similarly, this one will come and fill up this part. Okay, so these are the two conditions for what? For an effective collision. The first one, we say the particles mm, have to be correctly what? Orientated. Okay, orientated. And okay, the important part is what? Correct orientation. Important word, it is what? Correct orientation. Similarly, here it should be effective. This one is not necessarily that important for a examination question. I haven't seen them ask any kind of question related to that. But this one for effective collision, it can come, okay? For multiple choice, maybe, or just 1 mark. Okay, we are saying the particles have to be correctly orientated or yes, like that. And now the second one, we need one, the kinetic energy of the particles. Oh, sorry about writing. The kinetic energy uh, of particles, we need it to be greater or equal to, okay? Or equal to. Remember the activation energy, you need to overcome the activation energy. You need an energy to activate the reaction. So if you have an activation energy, you need an energy that is going to activate that. So this will come from the kinetic energy. If it is equal to the activation energy, your reaction will be active. Okay, it will be active. It will start to move, but in a slow manner. But now, if now it is greater like this, now they are moving faster. Okay, so it means now the reaction can occur, and the particles now are can collide effectively. So, but it is either it is because even if they are equal like this, they can still collide, right? But now this will just be the reaction rate will be much slower. Okay, yes, it will be effective, but it won't be that effective. So for it to be effective, you just need to be greater or equal, because both conditions are okay. That we are saying the kinetic energy of particles to be greater or equal to the what? To the activation energy. okay, of the reaction. Now, of the reaction. Or you can simply just say we need EK to be greater or equal to what? To EA. Okay? We just need that. Good. Now, remember we have talked about what are the conditions that are needed. This is very important. The important part is this one. You can do it in weights or this one. Now we have just said, okay, in a reaction, it means now the what we need for a reaction to occur. For a reaction to occur, we need a particles to collide. A reaction between two particles to occur, we need two those particles to collide, and we need them to collide effectively. Okay, but how can we make sure that the collision of it is effective? Now, by making sure that the orientation it is correct, okay, correct orientation, and now by making sure that the activation energy it is greater or equal to the what? To the activation energy thereof. Okay, yes. Now let's talk more about, because now this chapter now we're talking about it is more of a rate of reaction. Okay, yes. Okay, so now most of our questions will be based on the part that we are going to be looking at from here. Okay, now the first thing that we need to define it is the reaction rate. Okay, so we define a reaction rate simply, not that hard. We say now the reaction rate it is there. We say it is the change in concentration, okay, of reactants or products per what? Per unit time. This is going to be very important, this definition now, especially when it comes to per unit time. Now, it is the change in concentration of the reactant or product per what? Per unit time. So now, this definition automatically, it tells you, you can now derive a formula from this, saying now, the rate, it is the what? Saying now, you can say the rate is the what? They say it is the change in concentration of the reactants of product. Okay? Like this, change in concentration per what? Per unit time. Per unit time. This is very important. This per unit time is going to be very important from now in the definition up to when you are using this collision theory to analyze now factors that affect the reaction rate, the reasoning behind that. Okay, so now this is the rate as per definition, right? And now can you see now that the units for this one, remember for concentration it is mole per decimeter cubed per, remember this is always measured in seconds, right? This always, not sometimes, always in seconds. Okay, let me just always in seconds. Okay, here can you now see that the seconds are at the bottom, so I'm gonna say s minus 1 like that. Okay, now you can be given other formulas. It is not only applicable for changing in C. The other formulas that are still applicable is changing V divided by changing time, or you can also be given a changing number of moles, okay, divided by time, changing mass divided by time, depending on what you are given. But what the examiner will do, the examiner will say to you, calculate the rate of reaction in maybe in centimeter cubed per second. Now, can you see this is what is the measurement for what? For volume. So it means now the rate of reaction, the one that you're going to use, it is the one that has a volume. Or grams per second, it means you're going to be using the mass. So That is basically that, okay? Now, the interesting part, now let's talk about factors that affect the rate of reaction, okay? Now, we have to talk about these factors that affect that influences the rate of reaction. Now, the first one, it is the nature of reactants, okay? This one, do not stress more about it. They do not necessarily like to assess it, okay? Just that for multiple choice purpose, maybe, okay? So the first bullet says reactants in gas form a higher rate than solid. Okay, this is the multiple choice. It's very important. Maybe you are given a reaction of gas as well as the reaction of solids. They'll ask you which one has a higher a rate. Okay, then ions in solution have has higher rate than ionic solids. Okay, and the reason I'm saying do not stress this one a lot is because I know they do not like to assess it. Smaller molecules have higher rate than bigger ones. Okay, can you see now? These ones is not important. I want us to focus more on these from 2 to 5. Okay. Now, there is one thing that is going to happen throughout your journey in grade 12 as we are doing this chemistry part. Now, can you see now we are going to be talking about the factors that affect the rate of reaction, okay? The next topic that we're going to be dealing with, it is chemical equilibrium. It also has factors that affect chemical equilibrium, and concentration is one of them, temperature is one of them, catalyst is not one of them, surface area is not one of them. You're going to be confusing the reasoning, but I'll try to make sure that you do not, okay? Mhm. So let's look at this one. So they say now here for the concentration of reactants, now they say increases, it does what? It increases the number of particles that can collide effectively. Now, when we change the concentration, if we increase the concentration, what's going to happen? We increase the number of particles that can collide. Remember, particles we get them from the concentration. The concentration, it is a liquid. Okay, I do not want to say it is a liquid, but it is a solution. Okay, a concentration is a solution that has particles like a solution, let's say a solution that has particles, okay? Remember, even water has particles, okay? So now a solution, a concentration is a solution, and it has what? It has particles in it. So the more I add, let me take this down once here, okay? As I add As I add more concentration, can you see now I'm adding the what? The number of particles thereof. So there are more number of particles that are going to be colliding effectively. And we want a more particles, okay? Because during a reaction, maybe these particles has paired. Can you see that this one, it is just alone? There is no mate to pair with. So it means for this one, there's no reaction that is going to occur. But the more we add more concentration, increasing now the number of particles, it will get a mate, and those ones will get a mate. Now we are doing what? The reaction has no longer stopped. Here it was stopped because the reaction was complete again. But now as we add more of those concentration solution, we are increasing the reaction rate as it should continue. I want to believe you are following. Now, the higher the concentration, the higher the reaction rate. This is what I've just explained. Can you see now the reaction rate was okay higher, but now as we add more of these, they will be more high. This one I'll explain more thoroughly. Okay, do not worry about these ones. I'll explain just here. I'm just introducing you to the factors that affect the what? The reaction rate. Okay. The second one that we might look at, it is the temperature. Now, the temperature, remember when, okay, if we have, okay, it says it increases highlighter, increases the kinetic energy of colliding particles. Indeed. Remember now, let's talk about boiling water. This is a very nice example. Cold water, okay, then plus heat. And I'll just say plus heat like this. It will give me boiling. I want you to see boiling water. Now, do you all agree with me that boiling water, okay, what you don't know is that boiling water moves, right? But it is moving at a slow pace thereof. They are moving slow. The particles of water, cold water, they are moving slow. But you know immediately when you heat up that that pot with what with a heat, what happens, the water there boils, and now you see when the water boils it does this bubble stinging. No, can you see now the energy that the water has is now higher. It means now the particles now have what? The particles are colliding now effectively. So why? Because now they have kinetic energy. Remember, we need a kinetic energy that is greater or equal to the activation energy. Now, as we add temperature, we are increasing the kinetic energy. So the kinetic energy becomes more and more and more and more again. And now this is what is needed. Okay. So they now say the higher the temperature, the higher the rate. Yes, indeed, indeed. The rate here, it is slow because now they are moving slow towards one another. The collision is effective, but it is slow. But here the collision, like they just collide faster, faster as much as they possibly can, right? And now the minute this one collides, we have a what? A effective reaction. They collide effective reaction. So this one, if they collide slow, I don't know how to draw slow. They are coming to collide. They are about to collide. So now the reaction rate it is slower. They will eventually collide, but it is slower. An example that you can do it is when you have you can make this example, okay, at home whenever maybe you don't know it. If you're having cold water and hot water, if you pour, or rather if you put, okay, if you put a tea bag, let's say this is a tea bag. If you put a tea bag in here and a tea bag in here, now due to this one having a higher kinetic energy, the particles will collide more with the tea bag, all right? They will collide more with the tea bag, and then the tea bag will it will eventually become a brown fast, okay, faster. But here it will become a brown, but after a certain amount of time. So this is what we refer to the higher reaction rate. So can you see the reaction for this tea bag to become brown? It was faster, but for this one it was slower. I'm trying to explain this in a way that it will make sense. Even in an exam, you make a practical of these things, okay? Presence of a catalyst now, it decreases the EA of the kinetic energy. Now, remember, we need kinetic energy that is greater or equal to EA. Now, do you agree with me? As we decrease this, we are becoming happy because now it does what? If you are having, let's say the energy it is 50 joules, and now we are having maybe 51 joules. Okay, can you see that? Okay, we are having enough and greater kinetic energy, okay, for an equation, sorry, for a collision to occur. Okay, it occurs at a faster rate, but the minute I reduce this one to maybe something like that, can you see that more particles will have a much higher kinetic energy now? Okay, the kinetic energy will be much higher. Okay, yes. And remember, what does a catalyst do? Remember, a catalyst, it does what? It increases the reaction rate. So, of course, the addition of a reaction, it will now increase the reaction rate. But remember, what does a catalyst do? If I'm having a chemical reaction like that, remember what does a catalyst do? And this is what we call an activation energy. This. So a catalyst will come and be like, okay, I'm gonna reduce you like that. So can you see now our activation energy is lowered? Okay. And if it is lowered like that, it is what we need. That's what we need. Okay. So that the rate increases in the presence of a catalyst. Okay. The positive catalyst plus catalyst. Never mind that you'll never get a negative catalyst. Even if you do, which I doubt you will, it means now it decreases the reaction. But we always assume that the catalyst always does a positive catalyst. Okay, at least for now in our syllabus. Then we have surface area. Increases the number of particles that can collide effectively. Now, I want to explain this one thoroughly. Take this in a form of, okay, let's say we have a pill, ne? We have form of pill. Let's say we have, um, okay, a tablet, which is a pill, right? Can you see now a tablet? It is in this form, something like that. And you also have powder, not necessarily the powder, but tablets that are in a form of powder, right? Tablets that are in a form of powder. This one, it is in a form of, uh, I can say granule, or I can't remember the other word that they use. Granule or what? Ribbon. Okay, ribbon. Now the granule and ribbon are this form, but granule it is much bigger than the ribbon. Okay, sometimes they like to interchange this with, but just remember granule. Take note, granule it is greater than ribbon. Okay, yes. Now the same tablet, but now it is a form of powder. So it is the same tablet, but now in a form of what? Of powder. Okay, let's call this pill Hilme of five grams. It has the same mass. Okay, same mass here, 5 grams, five grams. Now, which one of these tablets between the two? The granule one, let's for now let's call it the solid one. Why? Let's call it the granule one, or the powder one will work faster in your digestive system thereof. Now, this is what is gonna happen. We know that this one, when it reaches your digestive system, it will have to mix with the saliva and mix with all the enzymes so that it can break down first. Remember, we cannot take this to our stomach as it is. So it means it should be digested first into what? Into smaller useful what? Useful pieces that are digestible. Okay? This is what we're gonna do. But for this one, they automatically, you do not need to break them because they are automatically in a form of powder. So they just mix with the saliva and enzymes. They just transport it to the what? To the stage one. We're gonna need another stage two where we bring this to the digestive system. I do not know how to draw digestive system, but this one they directly go to the what? To the digestive system. So can you see the reaction rate here? The reaction rate here it is higher, okay, but here it is lower because now we are using what? We are using a what? A sorry, what? Or a granule, right? And now another thing that's gonna happen is that, okay, you're gonna heal, right? Because you have used 5 grams of that powder. But if you use 10 grams of powder, do you agree with me that you're gonna heal more faster? Because now, why? Because now you have more of that same healing pill. Okay, so we might say it will heal you double of what it might have healed you when you used 5 grams, right? Yes. But now I want you to take note of something. Even though this is 5 grams, but if we were to change this to 10 grams, if you were to change this to 10 grams like that, let's say 10 grams like that, the reaction will be higher for this one. For this one will be lower. Why? Because at the end of the day, can you see now it has a higher mass? Okay, so there are many particles in here as compared to those. Okay, the particles will break out like this part will exact. If you are still using 5 grams, this one will exactly equal to the particles that this one have. But the problem is that this one has to be broken down first, whereas this one just need to be okay. So now sometimes they explain it in terms of surface area. Okay, so they like to say this one has a smaller surface area, this one has a what? A larger surface area. Can you see that? Can you see that? All right. I want to believe that you are following. So it says to us, surface area, what happened? Increases the number of particles that can collide. Okay, that can collide. But remember, if it is like this and it is like this, Can you see now there are many particles that can collide? The same tablet of the same mass. I should emphasize this, of the same mass. Uh, and this one, there are fewer particles that can collide because, yeah, it is just a granule, it's a solid thing. But this one is in a form of powder. There are more particles again that can collide effectively. Very important. So the greater the surface area, the higher the reaction rate. So the more you move from this one, from this tablet to what? To a powder. It means now you are increasing your what? Your surface area. Therefore, you're increasing the effective collision thereof. Okay. Yes. Now, sometimes you ask yourself, okay, if they talk about concentration, how am I gonna know if they talk about concentration? How am I gonna know if they're talking about uh, surface area? How am I gonna know if they're talking about the temperature or the what? Okay. So now one thing I want you to take note of is that, okay, for the concentration, this one occurs in a solution. Okay. Okay. Remember, in a solution, it can either be a what? Concentration. It can either be a solution. Okay. Solution. And not a solution as in like an answer. You should be knowing this, like maybe um yeah, solution like water. Water is a solution. Water, it is a solvent. Yeah. A solution, it is Oros. Oros, maybe it is a solution. Oros. Okay. Oros, the juice one, the juice. Oros. Oros. That one. Yes. It is a solution. And if you are given the the gas, also in gases, it works because now you'll translate it in terms of pressure in a way. Okay. But now I want you to take note of this formula, especially when you're gonna come to the reasoning part. Remember that concentration, it is equal to number of what? Number of moles divided by volume. This is a very important what a formula you need. Why? Can you see now, if we increase the concentration, we are increasing the what? The number of particles. This is what we explained. If you increase the number of particles, so if you increase the concentration, you increase the number of particles. Okay. Now, this is provided that this is constant, provided that the volume is constant. So it means when we reason for this, we're going to say now, and increasing the concentration increases the number of moles, okay? The number of particles per unit volume, per unit volume. Now, it is per volume. So it means now an increase in concentration will increase the number of particles per unit volume, because now considering that the volume is constant. Because if the volume were to increase, it will affect the concentration, okay? You have to remember that, okay? Yes. Um, Another thing that you can take note of again, okay? Now, if we were to if you are talking about the gases, ne? If you were to talk about the gas, if you increase if you decrease the volume, let me do this. If you decrease the volume here, if you decrease the volume, what are you gonna do? You're gonna increase the what? The concentration. Can you see? Can you see? And now let's say this becomes constant after being decreased. So this concentration has been increased. Ne? So what is gonna be done? The number of moles will number of particles will also increase. Okay, yes. So this is what we mean. Let me do a practical example for this one. If I'm having a volume of uh, a volume of 20 decimeter cubed and a volume of 5 decimeter cubed, and I pour now the same amount of oros. I can say a concentration of uh, 2 mole per decimeter cubed. This one, same amount of 2 moles per decimeter cubed. Now, can you see here? For this container, it will maybe be here, but for this container, it will maybe be here. Can you see now the number of particles in here? They are much more than the number of particles that are in here, because can you see there is a space that is left there? Yes. So this is more practical that we can take note of. Okay. Yes. 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 Okay. If we're talking about the solids, maybe if we were to talk about maybe the solids, okay. The solids, remember now, what do they do? We want to use a what? A powder form, okay? A powder form over a granule or a ribbon. You'll see when they talk about the magnesium ribbon, magnesium granules. So you see, they will talk about those things. Do not get confused when they talk about those things, okay? Uh, the temperature you can increase the temperature of when you talk about the gases, okay? When you talk about the gases, maybe what you can do, we can increase the what? The temperature, okay? And as we increase the temperature like that, it means now we are increasing the what? The kinetic energy thereof, okay? Now let's consider these two reactions, okay? Let me just create two reactions. Let me just create two reactions. Let me just say zinc in a form of solid plus 2 moles of hydrochloric acid, which they like to say it is in excess in most of the questions that you're going to come across. It's going to form us what? Zinc chloride in aqueous plus hydrogen gas. Okay, yes. Now, this, if you want to increase the effective collisions, this it is in solid, right? So it means now we have to use a powder here over a granule. Remember, we'd prefer to use a powder. But this is what concentration. Can you see aqueous? It is a concentration. What can I do to this concentration? It's either I increase the concentration, or another thing that I can do to increase the effective collision, it is I can do what? I can increase the temperature. Remember, it is a solution. So if I increase the temperature, it means now it is, yeah. Okay. This is what I can do on this reaction to increase the effective collision. Remember, I'm going to affect the reactants. Okay. Another thing that I can do, let's consider this reaction. H2 in a form of gas plus Cl2. This is also a gas, giving me 2 hydrochloric acid, 2 moles of hydrochloric acid, but in a form of gas. Okay. Now, what can I do to increase the reaction rate thereof here in this? Remember, I will affect the reaction, the reactants, rather. I mean, can you see here? This is gas. Okay, in gas, remember the gas. You can increase the what? You can increase the concentration, or what else you can also do, you increase the what? The temperature. Okay, so the temperature here does not necessarily work in solids, because if you're having a solid, maybe a tablet, if you heat it, how is it going to help you? If you heat it here? How is it going to help you? So what you want to do, you want to break it down instead of heating it, okay? But the concentration, you can heat it, you can add more of it. The gas, you can increase its concentration again, add more gas. By meaning increasing the concentration, it means now we can add more gas. Okay. When we add more gas, we are increasing the number of particles. Okay. Then when you increase the temperature of that gas, the particles will move at a constant. So I'm lying, not constant. At a higher kinetic energy, will move more vigorously. Okay. This one also applies for this one, since it is what? It is what? A gas. But now the important part is that a catalyst can be added in all. Okay? Catalyst can be added. Okay? In all cases. What you can do, you can add a catalyst here, a catalyst here, a catalyst there. A catalyst works everywhere. Okay? A catalyst works everywhere. Okay, I haven't. This is me just trying to make sure that you will understand, especially when you come sorry, I'm saying sorry, but I'm the one who's getting hurt. um, I'm just trying to explain the concept before I now move. Okay, now I'm starting to move now. Now I'm starting to move. You're gonna be having a nice day. Please, if you know that you are that particular person who becomes tired easily, you can give yourself breaks, right? Within this long video day off, you can give yourself breaks. Now, how can we measure the rate of reaction? We can see now. Okay, we are saying the reaction rate will be higher, the reaction rate will be lower. How do we know that? How do we know that? Okay. So they are saying for a reaction that liberates gas, that releases gas, the rate of the reaction can be determined by measuring the rate of gas liberation. Okay, they're just using big words, and we don't need big words here. We are doing science. All right. Now let's consider this reaction: zinc and hydrochloric acid forming me zinc chloride and H2O. Now I can measure the rate of reaction by looking at the amount of gas that is formed. In this reaction, it means now hydrogen will move in a form of gas, and you know, girls, not girls, I'm sorry. uh, gases can move anywhere, right? Remember, if I'm having a container, gases can move and go out. If this is an open a container, you know, gas will escape and move out like that, right? So let's consider this one. Okay. Now, on this one, we are trying to measure the gas, right? So we cannot measure this one in an open reaction. Why? In an open container, rather. If you use an open container, we won't know how much we have, because here it is zinc in a solid. There will be just gas escaping, so we will not have the results that we want. But if we rather input a syringe there, okay, a syringe that will do what? That will collect the gas. Remember, when the gas try to escape there, remember here, there will be a cotton wool here. Okay, remember this syringe will not be able to close all the burette here, if I may call it. So we need a rubber stopper, maybe. They use a rubber stopper, or yeah, I think rubber stopper is what they use. Yes, a rubber stopper. Okay. So now we are we inject that syringe in there. So it means now gas will move in this direction first, trying to escape, but there will be no way. So the only way will be to come there. Okay. Now let's say this is the measurement here. Let's say this is 60. Okay, as it is closed like that. Okay. But now, as air moves like that, can you see this air will put pressure on the syringe. So the syringe will blah 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 until the gas ends. Maybe the syringe will now be here. The reading. Can you see it is here now initially? And let's say at the end it will be somewhere here. Okay. Let's say it is 8. Okay, it has stopped at 8. Okay, now this will tell us, okay, the amount of volume that is produced, it is 60 minus 8, which is how much? Which is 8. So it means now we produced what? 30 what? Volume, it is measured in what? 30 centimeter cubes or meter cubes. Okay, of volume. Then we know we can use mole ratio to check how the amount of zinc that is left and the amount of hydrochloric that is left. Okay, yes, this is how we use that. Okay, and now in a graph, it will be like this. Now, there is a what? This is a volume. This is time graph, okay? Can you see that? Yes. Now, at time t0, there is no volume, right? Direction is it hasn't occurred, okay? But now, after direction has occurred, now we are measuring the what? Remember, we are measuring the what? The gas. Remember, the gas. Remember, initially there was no gas. Gas initial, let me say volume of gas, volume initial, I'll just say initial, it was 0. But now volume final, the amount of volume in here maybe is stated. Can you see now the volume increased? Okay, so the volume increased from here, it increased and increased, but initially they will reach equilibrium. Okay, there will be a point here. If you check T0, after T3, the reaction will continue being straight like that. So it means now our reaction has reached completion. Okay? Our reaction has reached completion. It means now there is no collision that is happening. There are no longer effective collision. There is no collision happening. It means now the reaction has stopped. But now I want you to check something. From T0 to T1, remember there are more particles, right? So they just collide faster. Okay? But as these ones collide, there will be few particles that are left. Okay? Those few particles that are left, they will try to find each other so that they can collide. So the more they are, okay, let me say the time that they take to find each other, it is longer. Okay, so if I'm having more particles like, okay, let me try to do it like this, maybe you'll understand it. If there are more particles like this, can you see they won't need time to just collide, they will just bump 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 bump. But let's say this portion has already bumped, ne? We are left with this portion, but remember this is particles, they can be like in this form. Can you see now? If they're like this now, they will try to from here to here, the distance to move there, which is the time, okay, in terms of time, it will be longer, okay? So the time for them to collide, it will be longer. So now it will decrease the what? The reaction rate. Remember the rate, it is what? The amount of something divided by per time. So if it takes longer for them to collide, it means now the rate will decrease, okay? But now if they are closed like that, like this, they take shorter period of time to meet each other. So it means the rate will be higher like that. People, I want to believe you are following. Okay, yes. So it will be like that. So the rate will decrease here. Can you see? Now the time it takes for them to collide, it is longer. So the time, as if the time is longer, it means now the rate will be lower. Will be lower there. Okay, will be lower there, will be lower there. Okay, then after T3, it means there are nothing that there are no more particles that can collide. It means now the reaction will reach completion. This is what this is explaining. I do not like to just point. Can you see T1? It is rate is increasing, but without giving you a reason why. Okay, so T1 we are saying it is the rate, it is higher. Can you see from T0 to T1 the rate is faster? Okay, but from T2, always when the reaction starts, at the start of the reaction where it just started, it is faster, the rate, okay? Whether it is a decreasing function or an increasing function, it is faster. But as time goes on between T1 and T2, in this region, the reaction uh, uh, becomes lower. But at T3, there is no reaction. So we are saying T, it is equal to 0. Sorry, the rate, it is equal to 0. Why? Because now the reaction has stopped. So there's no rate, okay? There is no rate. There is no change in volume now. Okay. Can we see that if there's no change, let's say change in volume divided by time, if now the volume was 30 here, was 30, so we're going to subtract 30 because it is now moving in a straight line, divided per time. So 0 divided per time, it is now 0. So this is what we are basically explaining there. Okay. Now, the one that I like the most is this one. Now, this is the original. Let's use the black one as the original, this one, okay? This is the original reaction. But now, the dotted one, this one here, that I'll do in blue, it is when the reaction is higher, okay? Why am I saying the reaction is higher there? Because the gradient is steep. If I'm having two things like this, if this one is like that, and the second one is like this, whether it, okay, let's say for now it ends there. This one, it means the reaction rate was faster, because I want you to check something. Let's say for this period of time, for this time t, let's see which one produces more gas. Okay, for this one, can you see here the black one produces that much, but the dotted line one produces higher. So if you produce a higher volume, it means now the reaction rate is higher. So this one has a higher reaction rate. Do not cram this. Try, if you're forgetting it, try to look it like that. For the same time, which one produces higher? If it produces again, yes. This one, it means it is lower here. So the rate, it is lower for this one, the bottom one, the red one that I'm doing. Okay, the reaction, it is low. I want you to check something. What they did here, maybe they increased maybe temperature or decreased temperature, okay, or increased or added a catalyst, okay, or yes. But now if they were to add, let's say we are still talking about this reaction, right? This reaction. If we were to add more zinc, if we add more zinc, if we add more zinc, now it means now the amount of volume that we're going to produce is going to be more. So it means the reaction will be higher, but we will produce more volume because now we have added zinc. Okay, yes. This I explained also in one of the multiple choice question under energy and change, exothermic and endothermic reactions. Okay, please go watch that video. It's going to be very important also for you. Okay, yes. Now let's see the explanation thereof. They say the dotted lines like this one, this one at the top, is obtained when the rate is increased. Can you see that? It means now the rate is higher. Why? By doing what? Maybe the temperature was increased, higher concentration, or add a catalyst. Okay, I'll try to avoid the nature of reaction. Okay, on this one, the it is obtained when the rate is decreased. So it means maybe they decrease temperature or concentration or what. Okay, yes. For this one, let's come to this experiment now. The other one, where we will be measuring now the okay. In this case, we are not measuring. In this case, we are measuring the what? The gas that escaped, right? In this case, we're gonna let the gas to escape. Now, as the gas escapes there, remember the gas formed from the what? From these two what reactants in a closed container. I want you to see this. If this container is closed and the reactants react and they form gas like that, they form gas like that. That okay. Let me use an example with the boiling water. If I'm having boiling water and I closed it with a whatever thing that you close it, the pot with, like this. Do you agree with me? The water will boil and boil, and there will be steam, the steam. But the steam will be here. And after being there at the top of that activity, the thing that closes the pot in English, it is the closer of the pot. I'm joking. But yeah, that thing that closes the pot now, it will have, do you agree with me? It will have drops of water there, and this water will go back to what? To the reactants. It will go back, and the reaction will continuously do that. Okay, it will be gas, and then after time it will cool down, water, from gas, water. That is what you call a closed reaction. So it means the reverse is equal to the forward. The forward is us forming gas, but this gas will also form water back, form gas, form water, like that. Okay. But if we let this carbon dioxide to escape in here, now it means now there is nothing that we can conserve back. So it means now this system is not isolated like that. So it means the mass of our reactants, the mass of our returns will increase, so will decrease, because why? We let portion of it, because this carbon dioxide is formed from these again. So it means now the mass of these reactants will decrease. Why? Because now we let the carbon dioxide escape. They might ask you why in a graph. In a graph, let's look at this graph. Okay, let's read here. They say the container takes place in an open container, okay, on a scale. Measure the mass of the reaction mixture regularly, okay? So the mass will decrease. Why? Because there is a carbon dioxide that is escaping, and carbon dioxide is formed from those reactants, okay? Now, the mass of the beaker and the contents decreases as the gas is. Okay, do not say it is the mass of calcium carbonate here, the one that you are measuring. It is not the mass of the solid, maybe. Maybe we'll say, okay, this is solid, is the mass of it. The mass of these reactants, of everything, will do what? Will decrease. The mass of the beaker and the contents decreases as the gas escapes from the beaker. Now, this is what I explained, right? Now, can you see now here it is decreasing? Let's say maybe it started with mass of 5 grams. They like 5 grams, since I'm also using 5 grams, 2 grams, 5 grams, 10 grams, that is what they like. Then it is decreasing like that. Decreasing. What is decreasing? It is the mass of the reactants. Decreasing, decreasing, decreasing until there is no more collisions that are happening. The rate is now equal to 0. Maybe the reaction has stopped. No more carbon dioxide escapes. Now it will be like that. Okay. So I want you to see something. Remember, I said when the reaction starts, whether it is increasing or decreasing, when the reaction starts, the reaction rate will be faster because now there is more content, there is more reactants. Can you see? But as time goes on, the reactants decreases. Why? Because there are some of the reactants that are lost due to over carbon dioxide, right? So the reaction rate slows down until now there are no. Okay, this one will be a limiting reagent. Okay, calcium carbonate will be a limiting reagent until now. Calcium carbonate finishes up. When calcium carbonate finishes up, there is nothing that hydrochloric acid can react with. So now the reaction will come into completion after T3 maybe. Okay, yes. I want to believe that is maybe clear. Let's look at the graph here. Here, here on the graph, the solid one, it is the original graph, right? But this one at the top, it is the one with what? With increased or decreased. Now we'll check. Agree here when we are forming, we are saying the one that form the most, that produces, let's say, that produce the most for the same interval. Which one produces the most? It is the one at the top, okay? So the one that produces the most is the one that has a reaction rate that is higher. So in that order, this one is the first one, the second one, third one, okay? But here, the one that decreases the mass more, okay? Can you see now here, maybe if this is 5 grams, which one decreases them? This one that decreases more. Okay, if the reaction rate is fast, it means more reaction will occur and more reactants will decrease. Okay, so this one has a higher reaction rate. Why? Because per unit time, or in that time interval, for that time, I don't know why it does not want to make a straight line. For that time, can you see now this one? This one has escaped, has or rather, let's translate it to it has produced more gas, because now if more reactants were lost, it means more gas was produced. Again, can you see? But for this one, for the second one, for that time interval, less. Okay, maybe more of them of the reactants were lost, so it means more carbon dioxide was formed. But for this one, less mass was lost. So it means less what? Less. Carbon dioxide was formed. Okay, yes. So this is still the same thing. It also applies for both these two. Okay, yes. I want to believe you are following that one. This is us talking in terms of graphs. They are very important. They can either give you this graph or that graph, but they will tell you which one is a limiting reagent, or they will ask you. Okay, they will ask you which one is a limiting reagent. Okay. Mm. Normally, HCl, it is in excess. Most of the time, 99.9% of the time, HCl, it is in excess. Okay, yes. Now, sometimes we can measure on how we see now whether the reaction has occurred or what, or it has stopped, or it has what, okay? How can we do that? Now, in a reaction where precipitate forms. Remember, a precipitate, it is a solid that forms, okay? A precipitate, it is a solid that forms when we mix reactants that do not like each other. All right. In a reaction where precipitate forms, now will form something like a solid. So it will form like a solid at the bottom. Can you see? Okay, for an example, if I'm having maybe a reaction of some concentration of something, then I add something there, then it forms it makes to form a solid there at the bottom, okay? So we are saying now the rate, okay, in a reaction where precipitate forms, the rate of the reaction can be determined by the rate at which the precipitate forms, okay? Yes. What do they mean by that? So we can know, okay, if the precipitate forms now, it means now the reaction has ended. Now, what we will measure here, we will measure the time in which it took for this precipitate to form. Now, what happens is that we place a paper. I'll try to draw that paper in a 3D shape. We place a paper and we put a cross like that. Okay, a cross like that. Then we do what? Here is that paper with a cross. Then we place a beaker. Okay, we place a beaker with a concentration. Okay, with a concentration that is visible for us to see. Okay, can you see now? It is visible for us to see here the cross. Okay, so we measure the time in which it took for the reaction to form precipitate. Remember, we said precipitate it is a solid. So when it forms that solid, the color will maybe change. Okay, then the cross will disappear. The minute the cross disappears, we stop the time. Let's say after 10 seconds. After 10 seconds, the the what the the precipitate forms. Now we can see how the rate was faster or slower. So if you say 1 divided by 10 seconds, remember rate, it is changing something divided by time. But this one, let's consider them as constant. Let's say change in concentration divided by change in time. But now the concentration is constant, you just put 1. Then the time, it is what? 10 seconds. So it means now the reaction, it is 0.1. Okay. But now let's say it took shorter time. Let's say it took shorter time, like 2 seconds. Let's see if it took, if it took, yo, let's say it took 0.2 seconds. Let's see how the rate is going to be affected. It's going to be 1 divided by 0.2 seconds. So you'll get something like 5. 5. Okay, so now can you see, if we take a shorter time, the reaction rate, it is faster. But if you take a longer time, the reaction rate, it is slower. So that is what you are supposed to understand the of. Okay? Yes. All right. Now what we can do ourselves a favor now, it is us in a position of yeah, maybe drawing the graphs. Okay, now let me do this. The graph uh, for okay, for time. Okay, time versus concentration of something. For most of your time, you're gonna encounter concentration being like this. This is concentration, okay? Those square brackets. So if we have the time and the concentration, so our graph will be like this. Okay? You don't need to know the graph, this graph here, okay? Or if I'm having maybe temperature here. Temperature here. Why? Because now, remember, the reason they are inversely proportional, it is because now, remember, as time, can you see now, the time decreases. The time decreases, okay? What happens to the time when what happens to the time when it sorry, what happens to the rate of reaction when the time decreases? The rate increases, okay? So it means now whatever the factors that we used there were fast. So it means we used the increased what temperature or concentration, okay? But if you were to draw the rate graph, and remember what is rate? Remember, rate, it is 1 divided by time. And concentration graph. When the concentration increases, what happens to the rate of the reaction? Remember, we said as we add more concentration, we increases the rate. Can you see now? But here it is time. Time and whatever the factors are inversely proportional, but the rate, it is directly proportional to the factors thereof. Now, you're going to come to explanation of factors in terms of collision theory. This one, they will ask you. This one, they will definitely ask you. Okay? So now let's start. If we talk about the surface area, how is it going to affect, okay? Or another word for or surface, oh, sorry. What did I do there? Okay. Another word for surface area, they might say, sorry. They might say state of division. Okay, yes. What do I mean state of division? Remember this one, it is in this state of division. This one, it is in this state of division. So just differs the state of division. This one, it is more divided into its components. This one is less divided, okay, or hardly divided. So how are you gonna use this in a form of explanation now? Okay, I'm gonna be using increase, okay? This also applies for the decrease. For the decrease, we just use vice versa of those words. Okay, I'll show you. So let's say now, we're talking about the surface area. Let's say now, the first thing that we use is now with the use of powder. Okay, with the use of powder. What is going to happen with the use of powder? Remember what I said? I said you prefer to use powder over what? Over granules. Okay. So now with the use of powder, how does this affect our what? Our reaction rate? Now you have to explain in terms of what? Of collision theory. So now, what you the first reasoning that you're gonna say it is now the surface area increases. Okay. Remember, if it is like this and if it is in powder, can you see now the surface area increases? Okay. You're gonna say the surface area increases. Okay. Now, if the surface area increases, then what will happen? More collision will take place, because if it is like this, there is no more collisions. But if it's like this, there will be more collisions. Okay. The surface area increases. Again, therefore, I want you to take note of something. If this is the surface area that has increased, can you see now there will be more effective collisions here? But now, how can we, which part of the effective collision will happen? Remember, for an effective collision to happen, we need kinetic energy that is greater or equal to EA, or we need the correct orientation. For this one, we cannot use kinetic energy because it is not temperature. Okay. Yes. So here we'll say, okay, if the surface area increases, the what? The orientation, more particles will have the correct orientation. With correct orientation. It's in life orientation. Okay. If now there is more particles with the correct orientation, now this is very important. They will be, remember, if we have this condition, correct orientation, it means now there is effective collision again. So it means now there will be more effective collision. Very important. More effective collision. Effective collision. Per what? Remember, this happens per time. Okay. This happens over time. So we say more effective collisions per unit time. You're gonna forget per unit time, you're gonna forget your marks. per unit time. Very important. Very, very important. You just say more effective collisions, fella. You are out. You lose a mark rate. Then now, how if you're having more effective collisions, how will this affect the rate? Now we'll say now a higher reaction rate. Okay, or you can say the reaction rate will increase. That is how we explain the surface area. Okay, normally it is 4 points. But if it is 3 marks, it means they already told you the reaction rate is high. Okay. Sometimes they will say, explain how the effect of the temperature or the effect of whatever that was added there will affect the reaction rate. Okay. And this, they can mix it with chemical equilibrium, you'll see, as time goes on. Now, for concentration, let's say now, a higher concentration is added, okay? At higher concentration, okay, increased concentration. If you're increasing the concentration now, then what will happen? Remember, every time when you think of concentration, you should think of this formula. Okay. Now, if you increase the concentration, remember I said per unit volume, the volume will be constant. You increase the concentration, you increase the what? The number of particles. Okay. So you'll say now, what you should think of is that there will be more particles per unit volume. Okay? Some more particles. We are increasing again the particles. So there will be more particles per unit volume. Okay? That is the first one. The second one, if there are more particles per unit volume, it means now the what? The orientation will be fine, Leon. Okay? So it means there will be more correct orientation. Okay? More correct what? Orientation. Okay? More particles. What did I say here? More particles with correct yes. More. Use the one that your teacher gives you, okay? Or the one that you get from the memos, okay? More, especially from the department question papers, okay? Yes. More particles with correct orientation. Remember, we need this. We need this. We need this. Why? Because remember, for an effective collision to occur, let me go back. We need, for effective collision between particles, we need correct orientation or okay, kinetic energy like that. But in this one, you can accept if you have one of those, it means now you are having a correct, an effective collision. Okay. If there are more particles with correct orientation, therefore it means now more effective collision. Okay. Per unit, per unit time. People will lose marks. When I'm highlighting per unit time. Therefore, what will happen to the reaction? Higher reaction rate rather. Higher reaction rate. Or you can just say the reaction rate will increase. Okay? Yes. Cool. Temperature. Let's talk about the temperature. Let's say what happens to the temperature now. Let's say at higher temperature. Okay? At higher temperature. So it means we have increased the temperature now. What will happen? Remember, how does a temperature, okay, what does a temperature affect? Remember, if I'm having water, remember for temperature, I used an example of water, cold water. If I heat this, what will happen? this water will be like blah 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 blah. The sound that it does, I don't know how to. I'm not water, but yes, it will move fast again. So it has increased the kinetic energy. The kinetic energy it is increased. So this will do what will affect the kinetic energy. Okay, so we'll say more particles. Oh, at higher temperature, the average kinetic energy, average kinetic energy of particles increase. Or you can say the particles now move faster. Okay. But now if they move faster, what will happen? If they move faster, so can you see now we are having more kinetic energy? So we'll say more particles. There will be more particles with kinetic energy that is greater or equal to that of the activation energy. Can you see now we have something for effective collision? Yes. So it means now the effective collision occurs. For these two, surface area and concentration, we used correct orientation. And it was one of the condition for what? For effective collision. Okay? It was one of the conditions. But now, can you see now for temperature, we are using what? Kinetic energy, the off. So we are saying kinetic, more particles with kinetic energy that is greater or equal to the activation energy. Then you'll say now more effective collisions. Aye, but mamdim. Hey, what? Hey. Hmm? You need time. The average kinetic energy, okay? Average kinetic energy of the particles, okay, increases, or the particles will move faster, okay? Now, if you have more effective collisions, it means now we'll have what? Higher reaction rate, okay? A catalyst is just a positive catalyst. What does a catalyst do? Remember, a catalyst a catalyst does what? Lowers the activation energy. So it provides a path of shorter, it provides a shorter, it provides a path of shorter route. Yeah, yeah. Let's see. How does this affect with the addition of catalyst? Okay, addition of catalyst. Let's say they added the catalyst. These are the effects. The ones that I'm writing are the response. Addition of a catalyst, they will what? It provides a shorter path for the particles. Okay, it provides a shorter path. Remember, the path was this long, but now it comes and provides a shorter path. Okay. Then now, if there is a shorter path now, remember there will be this. Okay, if this one is short, it means more particles will have a higher kinetic energy or a kinetic energy that is sufficient. Okay. Okay, so you'll say, here you can say, but more particles will have a sufficient. You have to say sufficient or enough kinetic energy. Okay, that is greater or equal to the activation energy. Okay, here you'll have what? Also more particles. Okay, more particles will have sufficient kinetic energy. Okay, sufficient kinetic energy that is greater or equal to the activation energy. Okay, if this one occurs, therefore more what effective collision. Every time when you write this statement, more effective collision, ask yourself per what? More effective collisions per what? Do not write per what. Per what? Per unit time. Therefore, higher reaction rate. This one will always be higher reaction rate. Okay, this one will always be higher reaction rate like that. For this one, we can use vice versa. What you can do instead, you can say, okay, if you use a granule or a ribbon, the surface area will decrease. We just change a few words. Can you see? Decreases less particles, again, less effective collision per unit time, lower reaction rate, or reaction rate decreases. Can you see? When we decrease concentration, less, can you see? When we decrease the concentration, there will be less number of moles per unit volume. Therefore, there will be less particles with correct orientation. There will be less effective collision. There will be low reaction rate, or the reaction rate will be high. You just need to know with increase. For the decrease, is just the reverse. Okay? At lower temperature or at decreased temperature, the average kinetic energy will decrease. Okay? If it is water, like cold water maybe, when you convert it back to ice, ice is not moving. It's moving. Oh, even a tortoise moves fast. Okay, therefore less particles. Okay, therefore less effective collisions. Okay, we are not saying there will not be effective collisions. There will be effective collisions, but there will be less particles that have the capability to do what? To have an effective collision. Okay, therefore low reaction rate. Just like that. Just like that. The last part now, okay? The last part now we have to deal with, it is the Maxwell-Boltzmann graph, okay? The Maxwell-Boltzmann graph. Now, the Maxwell-Boltzmann graph, it is a graph of number of particles or number of molecules, depending on what the examiner gives you, versus kinetic energy, okay? Against the kinetic energy, okay? So now, just take note that the graph now, the area under the graph now, it is what? Let's see the area under this graph. Okay. Okay, we'll talk about that. We'll talk about that. I'll come to that now. Okay, the area under the graph now tells us about the total number of particles. Okay, the total number of particles in that we have in this reaction. So these are the total number of particles. These ones. But can you see that? Or remember, this is kinetic energy. This is number of particles, okay? So here we have number of particles. Here it is the activation energy. Remember, the activation energy is the minimum energy needed for a chemical reaction to do what? Sorry, to okay, right? Yes. So never mind this one. This is the average kinetic energy, okay? Now, can you see now? Remember, for an effective collision, we need a kinetic energy that is greater or equal to the activation energy. But can you see this portion here? The kinetic energy here. The kinetic energy here. Remember, this is the kinetic energy, okay? This here, it is the kinetic energies, different kinetic energies, okay? It is the kinetic energy. But can you see now this one? The kinetic energy is less than the activation energy. This one will never have an effective collisions. These ones are the particles that do not, okay, with no effective collision. These are particles with no effective collision. Because why? Can you see now the kinetic energy there? It is less than the activation energy. And now you know that for a reaction to occur, at least we need to overcome the minimum kinetic energy. Okay? So now, okay, we are given here, okay, here is our activation energy. Okay, here is our activation energy. So it means now all the particles that are on the other side of the activation energy, like these ones are the one that will have what? That will undergo effective collision. Why? Because now they have what? They are the particles that have what? The kinetic energy that is greater or equal to activation energy. Okay, therefore there will be what? There will be effective or collision occurring there. Okay, this is very important. This is very important. They will ask you, maybe they will, in a graph, they will draw a graph like that, and they will ask you, what does this line, and maybe name it P. What does this line P mean? Remember, this line means this is what activation energy that we need to overcome so that we can have a what? Effective collisions. Okay? Yes. So these ones are the particles with no effective collision here. No effective collisions here. Okay. But now there can be factors that affect the what? The concentration. So the the reaction rate or the what? The effective collisions again. Now, still the same graph. Okay. What you have to remember here is, okay, similarly here I still have that activation energy. Okay. I'll make it here. This is still the activation energy. Let me use a different color. But now, can you see now? It means only these particles have what? Have effective collisions, right? But now we want to see the effect of a concentration. Let's say now we add, okay, this one, it is we add concentration. Okay, okay. This one we remove. I doubt you will encounter a question that you remove the concentration. Okay, but if you, okay, I want to use a different color so that it is different shapes. Okay, when you add the concentration, remember what does the concentration does? Remember as per formula. It means now when you increase the concentration, you increase the what? The number of particles. How can you do that? It means now you are increasing the number of particles. It means now your particles will now be like so. Okay, let me redraw that. You will have more particles. Can you see that? You will have what? More particles. Can you see that? They are now compared to this one. This one we had particles under this graph, but can you see under that graph and including this section also, it is now having a larger area. Okay? So you remember the area of this graph, the area, number of particles. Whether with effective or not effective collision, but it is what? Number of particles. Okay, so this one has more number of particles. Let's see how does this affect the what? The effect, the number of collisions per unit time. Can you see now? Okay, this portion of this graph, or this portion of this number of moles had effective collision, these ones. Okay, but can you see now with an effect of a increase in number of particles? Can you see now, including these ones, we now have new particles that have joined. Can you see now the particles with a kinetic energy is now higher? Can you see now it is now here? And at first it was where it was here. Can you see now there will be more particles with what? This means more particles or molecules, okay, with kinetic energy that is greater or equal to the activation energy. Again, yes. Now the question is, what if we decided to decrease? What if we decided to decrease the concentration? If we decrease the concentration, remember, C it is equal to N divided by V. If I decrease the concentration, I decrease the number of particles or molecules. So it's gonna be maybe something like this. Can you see? Now, can you see the ones with the kinetic energy that is greater or equal to the activation energy? They are now low. Okay, yes. So this is what you have to know, to understand. Okay, this one, more particles with EK that is greater or equal to EA. Here we have what? Remember, for this one, it is also that portion. Or rather, let me use a different color. For these ones, it is these, all of these, including those. Okay, let me do this. All of those, like that. So here we'll have what? Less particles with EK that is greater or equal to EA. Yes, they are, but they are less. Okay, they are less. Okay, this is how a concentration affects the graph. Okay, yes. In case you are asked to draw it. Now, how does the temperature? Okay, remember this is EA. Okay, how does now a temperature affect the number of particles? Just think about it. Just think about it. We said now, if the temperature is high, if the temperature is high, more particles will collide. Again, the kinetic energy will increase. Again, now the kinetic energy will increase. It means more particles will have what? Kinetic energy that is greater or equal to the activation energy. It means now these particles here. Let me do this. Okay, let me remove that. These particles here, since when they have a high kinetic energy, they will want to shift. They will want to shift to the right, because now they now have what? They will be like, hey, we now qualify to become in this side, because now we also have the what? The kinetic energy. So they will be like, let me say, increased temperature. Okay, increased temperature, it is rather color red. They will be like, hey, we now have kinetic energy that is sufficient for us to now collide effectively. So they will be like, hey, we're gonna jump to the other stage. So it means we also qualify to the other side. So it shifts to the right. Okay, your number of particles will shift to the right. Why? And your peak will be more to the right, but it will not be exactly that. It is not like this. Okay, they are shifting to the right, but with the same peak. No, your peak will be a little bit lowered, but the average kinetic energy of the particles increases, the temperature increases again. So the peak is more to the right, because can you see now more particles? Can you see now the ones that did not qualify were the one that qualified before were these ones, but now even these ones qualify now. Okay, so it shifts to the right like that. Okay, it shifts to the right like that. Okay. And now take note of something. The area under the graph remains constant. Like the area here is still the same. The particles are still the same. The number of particles in here are still the same than as those under the black color. Okay, unlike this one, the area increases, but for this one, the area remains constant. But what changes is that the peak is lower and broader. Okay, this one was thinner like this, but now it is. Can you see? Instead of doing it longer, we broaden it. We make it more wider, and we move it to the right. Okay. This is effect of an increased temperature. So let's say now we decrease the temperature. If we decrease the temperature, less particles will have what? Will have kinetic energy. Again, that is greater or equal to the activation energy. So particles will be like, I'm losing my energy now. My energy is now low and I do not qualify. Okay? Yes, I do not qualify to become in this effective collision site. So they will be like, okay. Many of us do not qualify. Let me redraw that. Many of us do not qualify, so it will be something like, let's just shift to the right. Okay, we shift to the right. Still, the area is still the same. The area is still the same. Can you see now? Can you see now? The peak is now much higher. Okay, much higher. Okay, so if you see a graph with a higher peak than the other one, just know the one with the higher peak, it is the one with the lower temperature, because now you can also see the one with the effective collisions. Can you see where they are here? Okay. Sometimes they may say the temperature is decreased. Draw the graph that will represent the effect on this Maxwell-Boltzmann graph. Okay, so it will just shift to the left. Okay, then your peak will be now longer. Okay, will be highest, and now your graph will be now narrower. Okay, it at an increased, your peak will be lowered and your graph will be broader, but for the decreasing temperature, it will be high. It will have the highest peak, but it will be narrower. Okay, yes, just like that. I just need you to know how to analyze these. They might ask you, what does the shaded area, shaded part represent? The shaded part represents what, if you were to tell me? It represents particles with kinetic energy that is greater or equal to EA. Okay? And what happens here? Effective collisions. Effective collision occurs in here. Okay? Yes. This is what we mean. Then let's move to the effect of a catalyst. This one is interesting. Okay, another thing to take note of, surface area does not affect the graph, okay? So there is no question that you'll encounter where they talk about surface area, okay? Yes, do not lie in an exam. This is the last part. So we are saying what happens. Now, you have to remember, just ask yourself, where is this is my EA. Okay, now you can ask yourself for, okay, if now there is an addition of a catalyst, there is an addition of a catalyst. What does a catalyst do? What I like to remind myself with is draw this graph and be like, hey, when a catalyst come, what will you do? Like, I'm gonna do this. That is what the catalyst does. So it'd be like, oh, I have done that. So what I have done, it is I have decreased the activation energy. Decreased the activation energy. So it means now the activation energy will be decreased. Can you see? It will be lowered. Okay. So it means now we will have a new activation energy, maybe somewhere here. New activation energy here. How does this help us? Now, can you see at first we had these having effective collision. Okay. But now, after a catalyst was added, can you see now we have more of those? Okay, this is not under the graph. We have more of those. Can you see that? So it'll be like, so it means catalyst does what? it increases now it makes the kinetic energy more particles to have a kinetic energy that is equal to it. So it means now, can you see, if these ones have the kinetic energy here, they will be like, we now have a kinetic energy that is exactly equal to the activation energy. But these ones that were here, that were struggling to enter that part, will be like, yo, we have a kinetic energy that is greater than the activation energy. We now qualify for what? For activation energy. So for effective collision, okay? So yes, this is what is happening there. The question that they like to ask about a catalyst, they will be like, okay, let me bring back that one. They will be like, what will happen to, let's say, P? They will draw a graph and say P. And be like, how is P going to be affected with the addition of a catalyst? With the addition, sorry, with the addition, my data is gone. My English data is gone. So hence the video is ending now. So what will happen to to P? Okay, to the line P. Line P will shift to the left. Okay, line line P will shift to the left. Okay, yes, line P will shift to the left. Okay, shift. Can you see? It was here. It shifted to the left. This is what the catalyst does. Okay. Mm, shift to the left, okay? Or the value. They might ask you, is the value of the new, if, okay, what will happen to the value of P after a new catalyst was added? Will it decrease, increase, or remain the same? Remember, if it goes to that side, it will do what? It will decrease. So people, that's all for the topic now of I summarized everything. Actually, I did not summarize. I taught you everything. Okay. If there is something that I'm not giving you, please leave it in the comment section. I'll attend that. I'll make a video special for you and be like, you left out this, you left out that. I'll touch it. Okay. So yes, thank you very much, folks. This is what I wanted to explain basically under a rate of reaction. Okay, so there will be a follow-up of many videos, probably 4 videos under this topic thereof, then so that we understand how these questions are asked, right? So now remember I said now the interesting part starts where we talk about the reaction rate here. Okay, now just remember the definition. The change in concentration of reactants or products. Do not say, oh, the examiner is saying reactants or products. I'll choose between the two. Now, write it as it is, as I wrote it here. The change in concentration of reactants or products. You miss this one, two or nothing. Two or nothing. This is a two or nothing definition. When you check the memo, it does this two or nothing. There's no 2 divided over 0 or hey, how does it happen that it gets more marks? No, it means now 2 or nothing. If you fail to say per unit time, you get 0 out of 2. If you state everything correct, it is 2 or 2. This means 2 or nothing. Good. So thank you very much, folks. I hope you understood the concept that I tried to explain from the graphs to all. These are the graphs of the rate of reaction, okay? The rate of reaction, okay? The rate of reaction there. But the ones that I just did are the Maxwell-Boltzmann's graph, okay? So thank you very much, folks. I hope you'll have now a greater now exams following up to you now understanding now some section of chemistry, which is a rate of reaction. It has a lot of marks. Something like it can worth 23 marks on your question paper. So please do not neglect it, or 28 marks. Okay. So please, people, make sure that you capitalize from these theory videos. Remember, chemistry, you need to understand your theory, okay, before you can do what you can apply it, okay? So yes, thank you very much, folks, for being with me. Thank you. I really appreciate it.